Hi, this is Mr. Barron, and I'm going to be showing you how to solve problem number 49 and 59 from chapter 15. Problem number 49 has the following chemical equation given to you. It's iodine reacting with bromine to produce 2-iodine bromide. All right, now I didn't write out what the states of matter are because they're all gases. It tells you you're dealing with a 1-liter flask. It does give you the equilibrium constant and concentration, which is 280. Don't forget that's a unitless number. And then they give you some initial information about the reaction. They say that you actually start with 0.5 moles of this, and then it's allowed to establish equilibrium, and then it wants you to tell you, or it wants you to figure out what the concentration of all three of these are at equilibrium. So I'm going to use an ICE table. I, of course, stands for what the initial concentration is. You're told you have 0.5 moles of this, and you're told that it's in a 1-liter flask. So in your head, you should be like, oh, well, molarity is what I need to fill in here because my equilibrium constant, K sub C, is for concentration. So what you're going to do is you're going to take 0.5 moles and divide it by the 1-liter flask because that's what you start with, and you end up getting, of course, 0.5 molarity. Now, I'm not going to write down a capital M because it might become messy in my ICE table if I have a lot of units that I'm dealing with as well as variables, unknown variables, because you're going to have one in this problem. So I'm just going to leave it like that for now. So let's talk about how this reaction changes when it's trying to establish equilibrium. C, of course, stands for change. Well, obviously, you only have IBR. That's it. And because you only have IBR, the equilibrium is actually going to shift. I didn't draw my arrow going back the other direction. It's going to shift, and you're going to end up producing some iodine and bromine in the reverse reaction until it establishes equilibrium. So because of that, you're actually going to lose iodine bromide. It's going to be converted into these two. So the amount that you lose, we don't know how much it's going to be, so I'm just going to write minus x. And we know these two are going to increase by some value x. Again, initially, they're both 0 because we started off with nothing but the IBR. Now, the important thing is whenever you're dealing with change, you really need to pay attention to stoichiometry. Always make sure you look at the coefficients in your chemical equation before you finish off writing out what the changes are. So if I'm paying attention to the stoichiometry in this problem, it's 2 of these for every 1 of those. So if I'm creating iodine and bromine from the iodine bromide, then what's going to happen is it's going to be 2 of these for every 1 of each of those. So I have to put a 2 in front of this x, so it's minus 2x right there for the change. Now what I'm going to have to do is write out how each of them are represented after equilibrium is established. 0 plus x is just x, 0 plus x is just x, and 0.5 minus 2x, I'm actually going to write that out. And again, that's in molarity. I'm just not writing that out to save on unit space. All right, now what I've got to do is I know my equilibrium constant. So let me write out the equilibrium constant in terms of my reactants and products. So it's IBR squared over iodine times bromine on the bottom. Remember, these powers are, of course, from the coefficients. Now what I'm going to do is I'm going to plug in x in the equilibrium constant here. So I'm going to plug in the 0.5 minus 2x in for IBR. So let me write that out. So it's going to be 0.5 minus 2x, and that's going to be squared over x times x, because those two are being plugged in there and there, and I get x squared. And that's going to be equal to the equilibrium constant, which is a given value that I know from the beginning of the question, which is 280. So I'm going to write 280 here. The cool thing is, of course, I can take the square root of both sides. And when I take the square root of both sides, those go away, and I'm left with the square root of 280 is equal to 0.5 minus 2x over x. Now, if you didn't understand why I crossed those out, don't forget that, again, this whole fraction is to the power of a half. And don't forget your rules of algebra if you have something to the power of a half or a power squared or power to 3 and you have a fraction and what that means for the fraction. All right, now what I'm going to do is I'm going to combine like terms and get x by itself. So let me actually go ahead and plug in what 280 is, the square root of it. So the square root of 280 is is 16.7, and that's going to be equal to 0.5 minus 2x over x. Now I got to get x by itself, so I'm going to move x to the other side. X's go away, so now I have 16.7x equal to 0.5 minus 2x. And I combine these like terms, so I'm going to add 2x on both sides. And when I do that, that goes away, and I'm left with 18.7x equals 0.5. Now I just have to solve for x, and then I know the concentration of everything at equilibrium. So of course it's going to be 0.5 divided by 18.7. When I do that, x is equal to 0.027. This needs to be plugged in for all the values for the equilibrium. So this number, watch my pen, I'm going to drag it up here. That number has to go in here for x there, and x there, and x there, and then I know the concentration of everything. So the concentration of iodine at equilibrium is that number that I solved for x, which is 0.027. Same for this one, it's 0.027. Those are my two answers for iodine and bromine. And then I have to plug that in and multiply it by 2 here. So it's going to be 0.5 minus 2 times 0.027, and the answer I get is 0.446. Now I did some serious rounding in this problem. If you guys got a different number because you were rounding to a different number of sig figs, that's okay as well. So again, we've got our answer right here, and each of these values are in molarity because we were dealing with K sub C, which is in concentration. If I was going to point out the most tricky part of this problem, it's this part right here where I made the decision to make that a 2. And that, of course, came from the coefficient in the chemical equation, because twice it takes 2 times the amount of iodine and bromide to form these two reactants. Now we're going to solve problem number 59. On problem 59, it's very similar to a lot of the other questions that are in chapter 15 dealing with equilibrium. The question involves the decomposition of this compound. And again, I'm not going to actually write out the states of matter just to save time, because if it's an equilibrium problem, you're usually dealing with everything either being aqueous or a gas. Otherwise, you have to ignore the solids and liquids, of course. So again, it's SO2Cl2, which is a gas, and then it's in equilibrium with SO2 and chlorine. Now the question's already balanced, so it's a convenient 1-to-1-to-1 ratio essentially, and then it tells you some given information. It tells you, and I'm going to break out the ice table for this one. So initial change in equilibrium. Initially, you begin with 1 molar of SO2Cl2. I know that because it tells you you begin with 2 moles of this reactant at 2 liters, which of course gives you your concentration of molarity. And I'm just going to write it out as 1. I'm not even going to write out the numbers. Now, it tells you that you don't have any of these products, so they're both initially 0. And then 56% of SO2Cl2 decomposes into SO2 and Cl2. And that's at, I believe they say that's at equilibrium. So what you're going to try and do is find out the equilibrium constant, which is K sub C. And K sub C at the end of this is going to be, of course, the concentration of SO2 at equilibrium times the concentration of Cl2 at equilibrium, all over the concentration of SO2Cl2. All right, so if 56% of 1 gets converted into the products at equilibrium, that means I lose 0.56 from this reactant. On the flip side, that means that I gain 0.56 for each, and that's because of the stoichiometry of this equation. Don't forget, C, you got to pay attention to the stoichiometry. For every one of these, produce one of this and one of that. So the numbers are going to be the same for each of them. The only difference is that I'm experiencing loss on this side, and I'm experiencing gain on this side. So I do my math, and I end up with 0.44 for the concentration of that reactant at equilibrium, and then 0.56 molarity for both of these. Now all you have to do is plug it into your equilibrium constant. So I'm going to take these numbers and go ahead and plug them in. So it's 0.56 times 0.56 divided by 0.44. I do my math, and then I find the equilibrium constant is 0.71. If you have any other questions, please let me know.